Hello everyone. This is the presentation for task 4 for the Cloud Lab course. So in this task, we are going to study the distributed transactions. Specifically, you're going to learn about single node transactions and how these are extended to distributed settings. In addition, we will study the two-phase commit protocol, which is a standardized way to materialize distributed transactions. Lastly, in this task, you will build your own end-to-end distributed key value store that also supports transactions. Let's start with a bit of background information. Transactions are nothing more than a set of operations that process massive datasets in an atomic manner. Transactions are great because they offer programmability, so we can process massive datasets in a serializable manner and thus ensure correctness. And in addition, they offer transparency and the view of unlimited resources. Lastly, distributed transactions and transactions in general need to be durable and recoverable, so any modification to the underlying data survive in case one or more nodes fail. Now let's talk about single node transactions, which are executed over a single node key value store. We say that transactions are ACID, which stands for the following four properties. Transaction needs to have the all or nothing property. They need to preserve a correct state of the system as if each of them had been executed serially. And lastly, they need to be durable and survive after a fault. Distributed transactions operate over a distributed set of machines that store the dataset in parts. Distributed transactions need to maintain, similarly to the single node transaction, these ACID properties in this distributed setting. In reality, distributed transactions is a mechanism where two or more machines need to agree to either do something or not do something. For example, if one node commits, then all participant nodes to this transaction should commit as well. Else, if one or more nodes fail, all nodes should abort. So the real challenge about transactions is how can we guarantee these ACID properties both in single node and distributed nodes. In both cases, there are some key ingredients that help us to achieve those properties. So first, in single node transactions, we have a concurrency control that resolves data races and serialized operations and helps us ensure isolation and consistency. And in addition, we also have a login mechanism or a login policy that helps us recover in case of a failure. Now, as far as the distributed transactions are concerned, we have a similar mechanism. We have a distributed concurrency control that achieves the same goal as in single node case. And also we have a distributed login mechanism to bookkeep the state changes in the system. However, as distributed transactions might touch data in more than one node that fail and operate independently from each other, we need a distributed atomic commit protocol to ensure the all or nothing property. Namely, that all involved nodes to a transaction will agree on the same outcome for this transaction. Now let's talk about the concurrency control. Briefly, there are three types of concurrency control. We have pessimistic concurrency control, like the two-phase locking, where operations take locks as they go along, and the locks are released after the transaction is completed, like it is committed or it is aborted. In addition, we have an optimistic concurrency control, where the operations are executed as if they didn't have any competitors, any data races, and a validation takes place at the commit time. Lastly, we have timestamp ordering concurrency controls, where operations are ordered based on a clock, on a global wall-time clock, or generated by the client timestamps. Now, single node transactions do not need to pass through any protocol because there is a single node that decides on the outcome of the transaction. However, for the distributed transactions, we need to pass through an atomic protocol to ensure distributed atomic commits. So the two-phase commit is a classical way to materialize distributed transactions. It comprises of two phases, a prepare and a commit phase. In the prepare phase, the involved nodes vote whether they want to commit or abort the transaction, and mainly the prepare phase ensures that if a node is about to commit, all involved nodes will commit as well. The commit phase, on the other hand, doesn't do any voting, but all nodes that participate on a transaction make the updates visible. For durability, usually there is a log that stores the current state of the system and the protocol for recoverability. Now we're going to see an execution example of the two-phase commit protocol along with the two-phase lock-in protocol. The two-phase commit protocol has coordinator nodes that drive the protocol and participant nodes. The client sends a transaction to the coordinator, and the coordinator forwards the respective request to the responsible nodes. Each participant takes a lock on the key and replies back to the coordinator with a success or a failure message. After the successful execution of the transaction, the coordinator needs to prepare the transaction. So it sends a prepare message to all involved participants, which mainly asks them if they can commit or abort. The participants log their vote to a log and reply back to the coordinator. Similarly, the coordinator logs the decision of the prepare phase, and then it proceeds to the commit phase or the abort phase, which is executed in a similar way. In a distributed system with transactions, we have two types of failures, participant failures and coordinator failures. So participant failures block the protocol, but if the transaction has not been prepared yet, the coordinator might time out and instruct the transaction to abort. Unfortunately, if the coordinator fails, the execution blocks forever. And that's one of the main disadvantages of the two-phase commit protocol. Now, when it comes to recovery, a node replaces its log to establish its latest state. For any uninterrupted transactions that took place before the crash but never completed, the recovered node might need to ask the coordinator about them. For example, in RocksDB, there is a write-ahead log to ensure that prior to updating the in-memory memtable, the write phase first persists the updates and the state changes to the log. Now we have said that the two-phase commit protocol might block if the coordinator fails. To avoid that, there are briefly two ways. The first option is to adopt the three-phase commit protocol, which introduces an extra phase. This extra phase notifies some participants about the coordinator's intention to commit or abort a transaction. And as a result, if the coordinator fails, one of these participants has enough knowledge to shepherd the protocol on its own. The second option is to use replication, similarly to task 3. So, in case the coordinator fails, a new node from the replication group can take over. Now let's see how distributed transactions with replications are working. Its gray box is a replicated set of nodes where it has a replicated key value store layer. Above the key value store layer, we run the replication protocol, which has a leader to coordinate the actions in the replication group. On top, we have the transactions layer that comprises of a log table and a transaction manager. The log table offers distributed locking and can be implemented in various ways. For example, we can have per shard locking tables, or we can use an external service like a Zookeeper. Lastly, on the very top, we run the two-phase commit protocol. So this is some extra material you might want to check. And to sum up, the fourth task is to implement a distributed key value store with transactions. Specifically, you will explore single node transactions and extend the mechanism to distributed nodes. For that, you would need to implement the two-phase commit protocol. For this task, we have no replication without replication. And in addition, lastly, you would need the coordination mechanism. For example, you would need to implement a two-phase locking protocol. So thanks for attending, and see you in the Q&A session.